I want to compare two different ways that we could do this correctly. So one way to do it would be to say, let's prove this for some arbitrary n, which is bigger than k, and not like set a concrete value for n, not say that n is specifically k plus 1. And so when we do that, okay, we kind of start with this stuff over here, and then we're hoping to get to this in the end over here. And what's important to note is this is what lets me say this, right? So that's our induction hypothesis right there. We assume that this is true for values of n that are less than k, n minus 1, or excuse me, values of k that are less than n. So n minus 1 would fall into that range of the induction hypothesis so that we can use this result over here on n minus 1. So now I've just plugged in, right, n minus 1 into both of those places for k because n minus 1 falls into this range over here. And then the rest of it is just some algebra that I'll just leave you to verify that gets us here. So that's one way to do it. And I would say, like, when you see problems like this, when like you're adding up a bunch of integers or something like that, I do think it helps to write out like the term that comes just before the last term so that you can see where the induction is going to come in. And I just want to compare the induction step above to the induction step here. So that I haven't done anything different with the base case, but here's an example where I could do this just as well by setting a concrete value for k plus 1. And so it looks very similar to what's going on up top. The difference really is that up top, we're thinking about the n minus 1 domino knocking over the n domino, whereas down here, we're thinking about domino k knocking over domino k plus 1. So it's really just like what we're calling the letter, essentially. But substantively, there's really nothing different about these two techniques. Maybe some questions about, you know, why are we using k or k plus 1 or n plus 1? Do you care which way we do? I don't really care. The book does s to the k implies s to the k plus 1, but you can do it in all of these different other ways. And I do think it's really good practice to be able to read proofs that are written differently. And so down here, I just put kind of bullets with what would be the inductive hypothesis versus thing that you want to show if you're doing it in these different ways. So this is the way kind of I've been doing it, which is to kind of show that S of k implies S of n for any value of n which is bigger than k. This is saying it doesn't necessarily need to be the next one that gets knocked over, but saying the smaller values imply the larger values. And this would be what it would look like how the textbook does it. So these are kind of all different ways of doing induction. Okay, basically what they're saying is one domino knocks over the next one in different ways. So they're all equivalent methods up to whether I use n, whether I use k, or whether I say k knocks over k plus 1 or k minus 1 knocks over k. They're all the same. So we're going to prove, right, every postage stamp of at least 8 cents can be made with stamps of 3 cents and 5 cents. We're going to prove this using induction, which is going to be the total amount of postage. So in this case, what is the base case that we would want to consider? So we're going to start with 8 cents, right? So we're not starting with 1 or 2 or 3, but this is say, prove that every postage amount of at least 8 cents. So this is telling us over here that n is bigger than or equal to 8. And we're going to assume here that we're not dealing with fractional, that we're just dealing with whole cents here. So if n is equal to 8 cents, how can we prove the base case? How do I get 8 cents on my envelope using 3 cents and 5 cent stamps?
One of each.
Okay, we take a 3 cent stamp, we take a 5 cent stamp, we put them both on. Then we've got some trouble, right? So we'd like to say, well, let's assume this is true for all values of k up to n, and then show it's true for the very next value. But there's an issue here in that if n is equal to 9, it's kind of a different case, right? It doesn't follow from the 8-cent case. So I don't see a way that I can use the fact that we just put 8 cents on this envelope to then say, okay, well, here's a way that you can take that previous result and now get 9. So if n equals 9, it's not going to really rely on what we just said about n equals 8, but we can put 9 cents of postage by putting 3-cent stamps. And then we have the same problem with 10 cents, right? And that is the fact that I was able to put 8 or 9 cents doesn't really help me figure out how to put 10 cents worth of stamps on it. But if we want to put 10 cents, then we can use 2 5-cent stamps. So here, the base case actually was not just one value that we needed to check. We needed to keep checking cases until we get to the point where now I can use a previous case to show that a later case is going to work. Then we'll come to the induction step next, because now we've got enough base cases to prove this in general. So now we're going to assume, does anyone see how we can prove this in just one more sentence is all we're going to need. So let me just do some scratch work over here. So let's say we assume that this works for smaller values of postage. So let's say this works for 27 cents, for 28 cents, for 29 cents. How could we show that, therefore, there's going to be a way to do this for 30 cents?
Because 30 cents is the 27-cent case plus another 3-cent stamp.
Here, what we can see is that it's not the domino that is immediately before 30 that knocks it over, but it's like this domino that's going to help us knock over the 30. So it's not the immediate case, but the case like 3 steps prior that's going to allow us to knock over all of the dominoes. If we take some integer bigger than k, then by induction, we know that we can make n minus 3 cents of postage. So here, since we needed to go 3 steps back over here, we had to show 3 base cases. Just kind of a couple of things to remember here, and that is that it's not always the prior domino that knocks over the very next one. And so it might be n minus 2 that knocks over n minus 3, n minus 1. So what we really want to do is show that as long as there's some previous domino, it doesn't need to be right before it, that's going to knock over a later one, then they're all going to fall down. Let's think about this one. So here we have a recursive sequence defined. So we have the first term is 1, second term is 3, and then after we set the first 2 terms, we define all of the rest of the terms based on that. We want to show that this sequence over here actually doesn't need to be defined recursively. It can be defined, it's equivalent to the sequence that I would get with this formula here. Kind of these recursively defined sequences, you're going to want to do as many base cases as things that initialize the process. Okay, so we'll prove this using induction. This is what we want to show for all natural numbers. Here, we're thinking about n as a natural number, so the base case would be 1. So we got the left side, which is a1 is defined as 1, and then if we want to prove this result, I can plug in 1 into that formula, and we get 1. But we're not ready to go on into the inductive step yet, because a sub 2 is also defined a little bit differently than all of the rest of them. So we got a sub 1 is special, a2 is special, and then all of the rest of them fall in the same bucket. So I want to prove both of these in my base case. Okay, so then we do our induction step. So now let's consider integers. And yeah, so here we'll start our case, not with 4, with 3. We've done case 1 and case 2. Okay, we're going to assume that the kth term in the sequence can be written as 2k minus 1. Yeah, so maybe I'll leave this here and we can kind of pick up with this example next time.